Hello, I am Ikram Nekkache, PhD student at Artois University in France and Farhat Abbas University in Algeria. Today I am going to present our research titled Towards a Compact Set-Based Encoding of Itemset Mining Tasks, which I did in collaboration with Dr. Jabbour, Professor Sais, and Professor Kamel. Firstly, I would like to start my presentation by giving the context of our research. After that, I will give an overview on itemset mining, followed by some elements of propositional logic. Secondly, before presenting our approach, I will present set-based encoding for itemset mining. Finally, I will discuss the experimental evaluation. Then, in the conclusion, I will recommend some research lines for future work. Data mining is the process of discovering interesting knowledge from large amounts of data. Clustering, classification, itemset mining, sequential pattern mining are few examples of data mining tasks. Itemset mining is a fundamental task in data mining to discover regularities between items. Initially proposed for the well-known market basket analysis application, now it's widely used in various fields such as marketing, bioinformatics, and network traffic analysis. Itemset mining approaches can be divided in two main categories: specialized approaches for extracting interesting itemset patterns such as a priori and FP growth. Unfortunately, most of the time these approaches require new implementations to take into account the user's constraints. Recently, new declarative approaches for data mining have been emerged by using the two well-known artificial intelligence models, constraint programming and SAT. We are interested in the question of SAT encoding for itemset mining. One of the major problems of SAT encoding for data mining is its size, which can be very large. Before presenting our approach, let me give you an overview on itemset mining. Given omega a set of items, an item set is a subset of omega, and the transaction database is a set of transactions where each transaction is identified by transaction identifier. Simply, a transaction is an item set. Here is an example of transaction database that contains 10 transactions divided over the set A, B, C, D, E, F, and G. Given the item set ABD, you can see that it appears 4 times in the transaction database, so its support is 4. The problem of itemset mining consists of enumerate the set of item sets that respect minimum support threshold. An item set I is frequent if its support is greater than or equal to a minimum support threshold. Now I will introduce some elements on propositional logic. This logic is defined as given a propositional variables noted by the letters P, Q, R, etc., logical constants and logical connectives. A literal is a propositional variable or its negation. A conjunctive normal form is a conjunction of clauses where a clause is the junction of literals. An assignment mu satisfies the model if it satisfies each clause. In this case, we say that the formula is satisfied, and in the opposite case, we say that the formula is unsatisfied. We denote the set of models by sigma. The problem of itemset mining have been encoded on set. More precisely, the authors proposed to associate to each item a propositional variable PA and to each transaction a variable QI. And to encode the problem, they add 4 constraints. For the cover is the first one, not QI equivalent to all the items that doesn't appear in the transaction. Simply, the idea is to capture that if an item not in the transaction is true, so the item set cannot appear in the transaction. The next constraints express the support, the frequency, and for more interesting item set they use the closure constraint. Here an example of the encoding. You can see they take items that doesn't appear in the transaction. Usually in transaction database, the number of items that appear is much lower than the items that doesn't appear. Generally, the number of clauses that corresponds to this constraint is almost equal to the size of transaction database times by the number of items. Clearly, for large databases, the size of this encoding will be also large, and SAT solvers cannot enumerate all models. Our objective is to minimize the total size of the SAT encoding, so to improve it, we propose to rewrite the constraints of this encoding. This constraint is a result of the cover constraint. It expresses that if PA is assigned to true, then all transactions variables are propagated to false. You can see in this encoding the subterm not Q3, not Q6, not Q9 appears 4 times. To make this encoding smaller, we substitute such subterm by introducing a new variable called R. We also include the definition of R, which is R implies the subterm. This process allows us to earn 5 clauses in total from the 12 clauses. We propose a new approach to identify efficiently the subterms shown in the previous slide. We define 2 values for each item A, FA and GA, where FA represents the first transaction containing the item A, and GA is the last transaction containing the item A. For this transaction database, the value FA corresponds to the 3rd transaction, and the value GA corresponds to the 9th transaction. For each transaction, we introduce 2 new variables, Ri and Si, to compress the encoding. We propose a propagation chain which allows us to propagate all Qi to false from I to M when Ri is set to true. And when PA is set to true, RGA is then assigned to true, and all the variables associated to transactions greater than GA are assigned to false. To significantly reduce the size of the encoding, one needs to find an ordering of transactions. The problem of finding the best transaction ordering can be seen as Boolean matrix compression. In fact, by considering a 0-1 formulation of the transaction database, our goal is to rearrange the matrix rows such that the 1 values of each row are as consecutive as possible. Therefore, we minimize the distance between the first and the last transaction containing A. The first 0-1 matrix is a representation of a transaction database. By reordering the transaction of the table 1, we can lead to matrix represented in table 2. The question is how to reorder the transaction database to compact the encoding size. Simply, the idea is to use the greedy approach. We recursively pick up the less frequent item in the current database, then all transactions containing this item are placed on the top of ordered database. This operation is repeated. Let's illustrate with an example how to reorder the database. On the left side, our transaction database, and on the right side, you find the transaction database ordered greedily. The less frequent item is the item A. We place the transactions containing the item A, which are T3, T9, T7, and T4, on the top of ordered database. Now we pick up the less frequent item in the remaining transactions, which is the item D. After that, the transaction 2 and 10 containing the item D take place in the ordered database. For the remaining transactions, we repeat these operations by considering the order of less frequent items H, F, E, G, and C. Then I will present the effect of this process of ordering the transaction database on the encoding size. In the worst case, the number of clauses is bounded by this formula and depends on the interval between FA and GA. Let us reconsider the obtained transaction database by applying the greedy approach. The associated chain of implications are illustrated on the left side of the table. And this is the complete encoding associated to the transaction database ordered greedily. As you can see, the size of the encoding is reduced. Now I present the experiments carried out to evaluate the performance of our approach. Our experiments were performed with datasets publicly available. The characteristics of the datasets are given in the next table. We used the well-known DPLL-based SAT solver Minisat adapted to enumerate all models. We propose to branch first the solver on the less frequent items variables. Now restart or conflict analysis are performed, and a simple backtrack is performed after each conflict or when a model is found. We compare the performances of our approach called CSAT-IM against Parasat Minor and two CP approaches, namely closed pattern and cover size. And we use different minimum support thresholds. According to the results, CSAT-IM outperforms Parasat Minor and the CP approaches on almost datasets, except for retail, where Parasat Minor outperforms CSAT-IM. As we can observe, using our approach, the number of clauses generated is clearly lower than Parasat Minor. Finally, for future work, we have two main lines of research to be explored. The first one is to improve our greedy approach by finding more better ordering heuristics. And the second one, we think it may be interesting to extend our approach for other data mining problems such as sequential pattern mining. Thanks for your attention.